Hi, I'm Jim Williams of Linear Technology, and I'm here today to talk about measuring switching regulator noise. People are packing switching regulators into more and more systems in tighter and tighter spaces, and they're concerned about noise coming out of the regulator. We're going to cover a lot of ground today. We're going to go very quickly, so don't worry, there's references at the end of the presentation. You can pick up the details and nuances of what I'm about to talk about. Okay, let's go to work. We're not really measuring noise at all. Noise is randomly occurring events. We're measuring coherent, harmonically related residue of switching regulator operation. It's directly related to the switch frequency and the harmonics of the switch frequency. Typically, 100 microvolt to 10 millivolt amplitudes are of interest in 100 megahertz bandwidth. Why 100 megahertz? Because the systems you're building are sensitive to wideband operation. Typically, the output of a switching regulator, what's referred to loosely as noise, takes a ramping form, which is directly related to the switch mode power delivery. There's harmonic content here, at the peaks, the inflection points, and a much wider frequency of bandwidth than the ramping. The measurement scheme we're going to use takes advantage of the residue small signal bandwidth by turning the entire measurement path into a 50 ohm system. This approach, turning everything into 50 ohms, has noise, bandwidth, and probe connection advantages. 50 ohms is just the way to go when you're trying to measure high speed at low noise. Dropping down to the bottom of the page here, the switching regulator is represented by this box to the left. We institute a 50 ohm coaxial measurement path with a back termination out of the switching regulator's dummy load, down a 50 ohm cable, through this AC coupled clamp. What's that? That's basically a capacitor and clamp diodes in a 50 ohm coaxial enclosure in front of the preamp. The preamp output feeds a 50 ohm scope, which is triggered by a flux sensing probe located above the magnetics of the switching regulator. And the reason I do this is to break up any potential path, ground loop path, between the scope and the regulator board, so there's no galvanic connection in the trigger connection. Before we get started with the actual noise measurement, you got to verify the signal path to make sure it really has 100 megahertz of bandwidth. It's got calibrated gain, and it's got absence of parasitic responses. To do this, we verify bandwidth by putting in a very fast rise time pulse and noting that the rise time is less than 3.5 nanoseconds, which corresponds to 100 megahertz bandwidth. These are the results when we do that. At 200 microvolts per division and 5 nanosecond horizontal per division, we can see we're coming in around 3 nanoseconds. That verifies we've got 100 megahertz of bandwidth. We verify calibrated gain by putting in a 1 millivolt, 1 megahertz square wave. And at 200 microvolts per division, we get exactly 5 divisions, which says our gain is calibrated. Incidentally, the fat portions in the flat trace region are not due to a defocused oscilloscope, but are the noise limits of the measurement, primarily due to the preamplifier. Now let's step over here to the bench and take a look at what we can do on a scope to make an actual noise measurement. Okay, we're here at the bench and we're actually going to measure some switching regulator noise. Let's take a look at what we've got for a setup. This is the actual switching regulator we're going to test. This big brown ugly resistor is the dummy load. This probe here is our floating galvanically isolated trigger probe, which comes over here to the trigger channel of the oscilloscope. Before we actually measure noise, we want to determine what our signal path residual noise looks like. With the power off at 100 microvolts per division, that's the noise defined by the preamplifier, about 100 microvolts. Now I turn the power on. You can just make out a silhouette in the noise. A little bit of parasitic zero signal noise, but nowhere near what we're about to measure for noise. So we're pretty safe on that account. Now let's move the signal channel from probe ground to signal. The ripple that we talked about earlier in the presentation becomes clearly delineated. You can see we're about at 100 microvolts per division, we're about 200 or 300 microvolts high. It's harder to see these wideband harmonics, which define the high frequency content in the waveform. If I go to a faster sweep speed, they become clear. This is about 500 microvolts of wideband harmonic, again in a 100 megahertz bandpass. This is how we measure switching regulator noise at Linear Tech. If you've got questions or comments, you can call me directly at Linear, or you can visit www.linear.com. Thanks for your time today.